Jai Hind to all. This is Dr. Naresh Kumar from Ajay Kumar Garg Engineering College, Ghaziabad. Welcome to the class of Optical Communication. In this class, we will discuss the basic concepts of electromagnetic mode theory, that is wave theory for the optical propagation. Basically, there are two types of theories to describe the propagation of light inside the optical fiber. One is known as the ray theory, in which generally we study like the principal total internal reflection, acceptance angle, numerical aperture, meridional ray, skew ray and their derivation, etc. Now another theory that is used for explaining the propagation of light is known as the electromagnetic mode theory, or also known as the wave theory of optical propagation, that we are discussing in this class. So first of all, what is the wave theory? Basically, light can be considered as a ray and that propagation is explained using the ray theory. But the ray theory has some limitations, like the ray theory is approximate theory. Ray theory can be applied only when the dimensions or size of the optical fiber is sufficiently large, and the ray theory is basically the approximate theory. To overcome these limitations, we prefer the wave theory. That is, we can say that in this case, the light propagation is explained by considering light as a wave, and this is more accurate theory as compared to the ray theory, and this can be applied even when the dimensions of the optical fiber is not sufficiently large. That's why to overcome the limitations of ray theory, we are using the wave theory. So for explaining the wave theory, we are considering the optical fiber structure as a cylindrical fiber. Cylindrical fiber or cylindrical fiber waveguide. That is, the wave propagation equation using the wave theory can be represented using the cylindrical geometry or cylindrical coordinate, and that will be explained in terms of, that is, r, phi and z, that we usually do for the cylindrical coordinate system. So the wave propagation equation can be represented using these three, r, phi and z. So next is electromagnetic mode theory or wave theory. As discussed, we are considering as a wave, and this wave of light will have a field component. This field component will be similar to the electric field component or magnetic field component as in the case of electromagnetic wave. So we can explain the propagation of light using the propagation of field component as in the case of EM wave. So the wave theory can be explained using the EM wave equation. So as we know that the basis of any electromagnetic wave or electromagnetic field is the Maxwell equations. So these are the fundamental Maxwell equations, like this one is known as the Faraday law, this one is known as the Ampere's law, del dot D equal to 0. In the case of free divergence, this is basically the Gauss law in the case of electric field, del dot B equal to 0, no free poles, this is the case for the Gauss law in the magnetic field. And these two equations are the relations between the electric field strength and the electric density, and magnetic field strength or magnetic field intensity with the magnetic field strength or magnetic density. And these are related with the medium parameters, epsilon that is permittivity and mu that is known as the permeability of the medium. Taking the curl of equation, that is using the Faraday law. So taking the curl on both sides of equation and putting the value using the next equation, that is using the Ampere's law. So we have putting this value in this case, and in the left hand side we get the cross product of three vectors A cross B cross C. After solving that we can get this one, and in the case of our equation, for this case we can get this one, because here the del dot E becomes equal to 0, because we have in the previous slide we have seen that del dot D equal to 0. So we will have del dot epsilon E equal to 0, epsilon into del dot equal to 0. This can't be 0, so this will be equal to 0. So putting that in this case, we will get this is the propagation equation in terms of electric field. In the similar way, if we take the curl of another equation and put the value of other equation, then we can get the wave propagation equation in the case of magnetic field, that is this one. This is similar to electric field wave propagation equation. So as the electric field or magnetic field propagates in the case of electromagnetic wave, similarly the field component in the case of optical wave also propagates, and this is the wave propagation equation, where this is the field component. This chi is representing the field component, and this Vp is the phase velocity or velocity of propagation. This is given by this one, putting the standard value, and if we take the standard value of mu naught and epsilon naught, that is the velocity of light. Now the wave propagation equation can be represented either into the Cartesian coordinate xyz, or as discussed for the case of cylindrical fiber, this can be represented in terms of r, phi and z, when the optical fiber is considered as a cylindrical fiber or cylindrical waveguide. And the solution for these wave propagation equation can be represented in the exponential form, like we have chi equal to chi naught exponential j omega t minus k dot r, where this r is the direction of propagation and this k is known as the wave propagation constant or vacuum propagation constant, given by 2 pi by lambda. So the necessary condition for the wave propagation is phase shift or phase change. So where this k have this one, but in the case of, this is for the case of vacuum. For the case of any medium, we will represent this as beta, beta as refractive index of that medium into k. So the phase factor or propagation constant will be modified with the value of the refractive index in that medium. So next topic is modes in a planar guide. Basically mode means, as we have seen in the previous slide, that the optical field component inside the optical fiber is propagating, and this field component after entering the optical fiber makes a particular type of pattern, shape or distribution. This distribution of field component inside the optical fiber is known as the mode. For example, this is the optical fiber and the field component inside this fiber is taking this type of particular shape. So this is known as the mode. Okay, so what is planar guide? Planar guide is basically the simplest form of optical waveguide. So for the optical fiber, what we require? We require simply is a refractive index N1 and another layer of lower refractive index N2, where this we have N1 is greater than N2. So if we have to make a simplest optical fiber structure, we will take the dielectric slabs. We will take a simple dielectric slab having refractive index N1. Now this dielectric slab of refractive index N1 will be sandwiched between two layers of lower refractive index known as N2. So where we have N1 greater than N2. So if we have a dielectric slab of refractive index N1 is sandwiched between two layers of lower refractive index N2, then that optical fiber structure is known as the planar guide. So as this is a simplest structure, so it will have only the simple modes. This is the propagation. Here light is considered as a wave resolved into two components, and it is propagating through the optical fiber cable through the total internal reflection along with the phase shift, and beta is in the z direction N1k and sin theta and cos theta, and in terms of core it will be N2k. So beta will lie between N1k and N2k. So in the case of planar guide, we have the wave propagating through the optical fiber cable, that is wave vector. Here basically we have some equiphase points. These are the equiphase points which combine together or join together to form a wave front, and this wave front travels inside the optical fiber with a velocity known as the phase velocity. So the wave propagates in terms of wave fronts, and this is the corresponding field pattern distribution inside the optical fiber cable. This is known as the mode. And as the planar guide is basically generally a simple structure, so due to simple structure, here only the transverse mode exists inside the planar guide. Only the transverse mode exists inside the planar guide. As clear from the name, transverse is perpendicular in nature. If z is the direction of propagation, we will have only the x component or y component for the electric field, or similarly for the magnetic field. Or we can say that for z is the direction of propagation, we have Ez and Hz equal to 0. So transverse mode we will have only, like for example, transverse electric and transverse magnetic. And as the planar guide is there, single plane is there, so single subscript m is enough for denoting the order of the mode. So this small m basically represents the order of mode. Okay. So this is one example of mode present in the planar guide. So this is transverse electric mode, this is also transverse electric mode, this is also transverse electric mode, but the value of m is changing, that is order of the mode. So we can see that higher the order of the mode, more is the penetration in the cladding, and we know that light penetrated into the cladding is not the useful light, it is eventually lost in the form of heat or radiation. So more is the order of the mode, more is the penetration into the cladding, and more are the cladding losses. So if we have m equal to 2, then we have slightly less penetration into the cladding, and when we have m equal to 1, further the penetration into the cladding is reduced. So, if we have to minimize the losses or penetration into the cladding, we need to operate with lower order modes. So, practically we should have lower order of the modes to have the less cladding losses. Next is phase velocity or group velocity. Basically, as we have discussed, the necessary condition for the wave propagation inside the optical fiber is total internal reflection along with the phase shift. So, whenever there will be phase shift, the wave will propagate and velocity is known as the phase velocity, and we know that this phase velocity Vp is given by omega by beta. We know that omega is angular frequency 2 pi f, whereas beta is this 2 pi by lambda. Okay, or we can also write beta, if for a particular medium it can be n1. So 2 pi to 2 pi, f lambda is c, so it is c by n1. So the phase velocity is given by the c by n1, that is velocity of light is reduced or affected by the refractive index of in that particular medium. So the propagation velocity is changed according to the refractive index of the core. Similar to phase velocity, we have a group velocity. Basically, what happens is, in practical cases, the single wave does not propagate. Usually, we have a number of waves combined together and propagating together. So, this is the one example. Here we have two waves. One is this one and another is this one. These two waves have similar characteristics or they have matching frequency, nearly equal frequencies. So, two waves having similar characteristics, for example, nearly equal frequencies, are combined together to form a package, group or envelope. And this group of waves or package or envelopes propagates with a velocity known as the group velocity. That is, here the waves having similar characteristics, for example, two waves having nearly equal frequencies are combined together to form a package, envelope or group, and these travel with a velocity known as the group velocity. So, this group velocity Vg is denoted by del omega by del beta, and as we have represented this phase velocity Vp equal to c by n1, in the similar way we can represent group velocity Vg equal to c by ng, where this capital Ng is known as the group index. The derivation for the same is represented here, and we can represent as group velocity as c by ng. Another topic is phase shift with total internal reflection and the evanescent field. So, basically, for the wave to propagate, there are necessary conditions TIR and phase shift or phase change. So, here we have denser medium or cladding, core N1, rare medium or cladding, that is N2. So, here we have a incident wave having magnitude A0. So, whenever this wave goes to the core cladding interface, some part of this light will penetrate into the cladding, denoted by the magnitude B0, and maximum part will be reflected back due to TIR, total internal reflection. So the magnitude after reflection we are getting is C naught. And after reflection there is change of direction. So we have minus J to be changed with plus J. Another condition for propagation is phase shift or phase change. So here we have beta x1 and after reflection it is beta of x2. So there is phase shift or phase change. As Z is the direction of propagation, so due to transverse direction we can have these component as either in the direction of x and y. That's why we have put it the x in the end, or we can put as y in the end. Now this field component that is penetrated into the cladding, the field component penetrated into the cladding corresponding to the mode has been given a special name which is known as the evanescent field. Okay, that means the field component penetrated into the cladding is given by the name evanescent field. So this is known as the evanescent field. Okay, so the field component penetrated into the cladding is eventually lost in the form of heat or radiation. So it's a kind of cladding loss. So it should be minimized. This is the diagram to describe the evanescent field. That is, this is the field component corresponding to the optical mode, and the field component penetrated into the cladding is this one. And we have given the special name known as the evanescent field. And we can see that this evanescent field is exponentially decaying in nature. So along the thickness of the cladding, the evanescent field keep on decreasing and eventually it is lost in the form of heat or radiation. So we can see that this evanescent field is a exponentially decaying component. As light into the cladding is unwanted, so it should be minimized. So how we can minimize it? So these are the some techniques or methods through which we can minimize the evanescent field or the penetration of light into the cladding. So first can be the cladding can be made transparent so that light can be escape out easily. Second is by choosing the cladding material suitably and having sufficient thickness so that it is gradually reduced to a negligible amount, or it should be made up of a material such that the absorption by the cladding is minimized. Another is we can operate the optical fiber with lower order modes, keeping the value of m minimum. We can minimize the evanescent field. In the previous slide we have seen that more is the order of the mode, more is the penetration in the cladding. So to reduce the evanescent field, we can operate with minimum value of m. Another effect that can be observed into the optical fibers is known as the gauge horn chain shift. This gauge horn chain shift is also known as the lateral shift, or sometimes also known as lateral displacement. This phenomena has been given the name based upon the scientist who has observed this gauge horn chain effect. Basically, this can be observed only by careful observation. Okay, so when we carefully observe the reflection of light at the core cladding interface, it is usually seen that the reflection is immediately at the core cladding interface. But in practical cases, light before reflection enters into the cladding. That is, to certain depth the light enters into the cladding, and after that the light is reflected back into the core from a virtual reflecting plane, due to which there is a some slight distance gap between the incident ray and the reflected ray. This gap is basically known as the Gauge-Horn-Chain shift or lateral shift or lateral displacement. We will see this in diagram. Here we can see that this is the incident light, this is the core cladding interface. Okay, so in theoretical cases we consider that this incident light is reflected back, immediately from this core cladding interface. But in practical cases, the light slightly enters into the cladding and then it is reflected back into the core. So the actual reflection take place from a virtual reflecting plane which is inside the cladding, not at the actual core cladding interface. So whenever the reflection point is this one, so there is a gap between the incident ray and the reflected ray, or we can say that the incident light or reflected light. So this gap in terms of distance between the incident light and the reflected light due to reflection of light after penetrating into the cladding from a virtual reflecting plane is known as the lateral shift, lateral displacement or Gauge-Horn-Chain shift. Although the value of this d is generally negligible, this d is practically observed as nearly equal to 0.06 to 0.10 micrometer, and this is observed at a wavelength of 0.55 micrometer. This is observed for a silver interfaced glass. Okay, so this lateral displacement or lateral shift or Gauge-Horn-Chain shift can be observed when it is observed carefully into the laboratory, and this is a minimum value. So that's all for this lecture. Thank you everyone. Jai Hind. These are the references used in the lecture. Thank you.